Hi, welcome to the thrilling part 2 of the Introduction to NLP video series. So in this video, I'll be using Python to show you some examples of tf-idf vectorization and logistic regression based on those vectors. For the actual Python interface, I'll be using Jupyter. I'll be using Jupyter Lab. In case you're not familiar with Jupyter, it's basically a nice browser-based front end for Python. So everything here will be valid Python code. The only thing that I really can't do in a standard Python interpreter that I can do here is to interactively plot images. Now Jupyter does give me a little bit of extra ability. I can sort of go back and easily copy and paste and rerun individual statements or blocks of statements. You'll see in the examples. So let's get started by loading some data. So I'm going to load in some news articles, and what I have done is that I have scraped about 24 news articles from today, and one of the stories today was that Joe Biden gave a speech in Philadelphia about his presidential candidacy, and I took 12 articles about that event and then 12 articles from the same news sources, the same domain names, but about different topics. And I'm going to try to train a classifier that can learn to distinguish between articles about the Joe Biden event versus random other articles from the same sources in the same day. The reason I chose the same sources in the same day is to, not make it too obvious. Like if all of my Joe Biden articles were from the New York Times and then I choose a bunch of other articles from the Washington Post, it might learn to distinguish Times versus Post. And I want it, the only variable that really changes, to be what the topic of the article is, as opposed to something else like when the articles were from or which sources they were from. Okay, so I have one file here called yes articles, and the internal format for that is actually as a Python string. So I'm going to open this article using Python's open command, and then I'm going to use Python's eval command to actually evaluate the contents of that as Python code. In this case, it's just data. So let's take a look at what the data format here. I have 12 yes documents. Yes meaning these are positive examples of the Joe Biden topic. If I look at the first article here, it has the URL. It's a list with a URL and some text. And if I want to just look at the article, let's print out the first 200 characters. And if I were to make it look a little more like the original article, this will print out the new lines instead of a \n here. So here you can see the beginning of that article. And let's take a look at an example of an unrelated article in the no docs list. So this is a warning about commercial airliners flying over the Persian Gulf. Okay, so first I will tokenize, because I want to show you an example of what tokenization looks like. So I'll get one specific article, the first article out. Right now it's just a string. I'll lower it, lowercase it. So let's look at the beginning of that string now. All lowercased. Next, we will remove punctuation. There are more sophisticated ways to get a list of punctuation. This is a very straightforward list of standard punctuation characters. Unicode adds a lot more. So here's a simple way that I can remove punctuation. I'll replace each punctuation character with a space character. And we'll look at the first 200 characters now. So what's an example here? Oh, there's a comma after Saturday that has turned into a space. Okay, there's one example. And finally, I will split this into a list of words on white space. So this is not the only way to tokenize by a long shot. Here we have individual tokens. There are many different choices. I could have stemmed or lemmatized the words. I could have excluded stop words. I could have split the words into pieces according to popular suffixes like ing, for example. There are a lot of choices here. But this is a nice basic thing I can do without even using anything in Python except the string module. So pretty straightforward. And next, what I want to do is I'll show you an easy way to get a bag of words vector for this article. So I'm going to get a unique tokens list by just converting the tokens into a set and then into a list. Now that, I'll show you the beginning of that list of unique tokens. Why did I convert to a set and then to a list? Well, because I want to have a vocabulary. And if I treat my full token list as a vocabulary, as you can see, there's redundancies. The word the, for example, probably occurs in that list multiple times, whereas in my vocabulary, I would like one slot for each word. Each word only occurs once. All right, now if I were to make a bag of words vector out of this article that determined my vocabulary, it would be boring. It would be all ones. So I'm going to have to get a different article. I'll call this article 2. And I will, let's print out the first few hundred characters. So here's article 2. And I'll just standardize the function to get the token list so you can see all the steps at once. If we remember, the first step was that we lowercased everything. And then we removed the punctuation by replacing it with space characters. And then I'll split. When you call the split method in Python on a string, you can give it an argument. You can give it like a new line character, for example. If you give it no arguments, it splits on all contiguous blocks of white space. So let's get the, I'll call this tokens 2 as the token list from article 2. So let's look at the first few tokens there. U.S. diplomats warned Saturday. All right, so there we go. And what I can do now is I'll call this vec2 because I'm consistently putting 2 at the end of everything for article 2. And I'm going to look at all the vocab terms. And if it's in the list of tokens, that'll be a 1, or otherwise it'll be a 0. For vocab term in unique tokens. Right. So let's look at the beginning of vec2 here. So this only has one word that's shared by the two of them, and we can actually find out what that, let's see, that'll be index 7. And oops. Yes, index 7 is a 1, and let's see which of those terms that is. That's the word world. That actually makes a lot of sense. The word world is in both articles. Okay, so vec2, this is a a bag of words representation, the Boolean version of a bag of words, where it's a 1 or a 0. Okay, so that's pretty fun. And now what I could do if I want to find a tf-idf vectorization, let's look at, I wonder how many times the word world occurs in the second. Let's see, I think I can, yeah, I think there's a count function here. let's see. Oh, it occurs twice. Okay, great. So the document frequency here of the word world is 2. I'm sorry, that's the term frequency in that first article. Now what's the document frequency? And let's look at all documents. So I'm going to put all documents in one place. So let's just make one big list. And actually, I think I'll start with the no docs first. And then we'll append to that the yes docs. Just a quick sanity check. We should have 24 items there. All right. And then the question is, how many documents, I'll write this out. How many documents contain the word world? All right, let's find out. All right, 8. Okay, so our document frequency for the word world is going to be 8 out of 24, which is conveniently just 1/3. So that means that our tf-idf score is going to be effectively 3 times 2 equals 6. All right, now that's based on the most basic formula that I provided. That's going to be tf divided by df. Well, I guess I just wrote that same thing twice, but so it's going to be 2 divided by 1/3 is 6. There are more complicated formulas, just to refresh your memory. Like some people add a 1 down here to avoid division by 0. Some people take logs. You could add 1 in other places. Let's keep the math consistent there. So now in practice, you probably don't want to do that work by hand in Python, and SKlearn has some great tools that make it super easy. So we are going to import from SKlearn a vectorizer. And you might be very surprised to learn that it's called a tf-idf vectorizer. That's a joke. It's very predictable. When you launch your vectorizer, I'll show you one of the fun features of Jupyter. You can hit Shift-Tab to, oops, I haven't. If there's a recognized symbol, you hit Shift-Tab, and it will give you basically the help string for that object, whatever that object is. In this case, it's a class tf-idf vectorizer, and we can give it a lot of options. I will give it just one of the most common options here is to specify the minimum document frequency, because the vectorizer here both determines our vocabulary as well as builds up the document frequency scores for that vocabulary based on a training step that we will do next. So I'm going to use this vectorizer to fit transform on all docs. Now let me tell you something about SKlearn. It has a very nice standard interface that covers basically all of the supervised models, many of the unsupervised models, and a lot of the vectorizers. So in particular, there are 2 methods that are very common: fit and transform. And there's sometimes a combined version, as we're seeing here, called fit transform, which I just ran. When you run fit on a SKlearn model, this is an easy way to remember what they do. Fit will change the model. It usually trains it. Okay, so that's how you think of fit. Fit changes the instance you're calling it on. Transform doesn't. So if you call just transform by itself, transform is basically implying the model knows how to do what you want to do, and transform will return a value to you based on what it already knows. So fit changes the model. Transform doesn't, but it returns a value. Okay. Fit transform does both. So fit transform means I am both training and I want the output right away. So in the case of tf-idf, let's take a look at what we've got back. So what we have is a sparse matrix. I don't really like sparse matrices because they're a little harder to work with in my opinion. So we are going to change this to a dense matrix by using the toArray method. And now you can see the type pair has changed from a CSR matrix, that's a compressed sparse row matrix, which means that it thinks of the matrix as a list of rows. Each row is sparse, meaning that it doesn't store the 0 values. And I've converted this to a dense array, meaning we do store the 0 values, but it's easier to work with. Okay, and we can see what the shape of that matrix is. It is a 24 by 1655 matrix, meaning that we have 1,655 words in our vocabulary. And in fact, we can take a look at those words. So the words are stored on the vectorizer themselves, and you can use the get feature names method. Let's see if it tells us here. It doesn't tell us very clearly in the help string. We'll just call it and just take a look at the first 10 words. They are stored alphabetically. Let's take a look at the last 10 words to see some non-numerical words. So here are some of the words that the vectorizer chose for us using all of the documents. We could try to look at tf-idf, but the actual matrix is huge, and it's not obvious how to visualize that based on these numbers. Okay, so I'm going to import matplotlib and use that as a way to visualize things. Okay, that's kind of a standard way to use it in Jupyter. I'm going to increase the figure size a little bit just to make sure that everything here is pretty visible. So imshow is one way that we can visualize a large matrix. So this is a pretty flat matrix. We can see a few lines showing up. These are going to be the more common but also meaningful words. So I don't know what this word is. It'll be interesting to see what that word is. Over here we see an interesting little half line. Half lines are great because the top articles are no articles. The bottom articles are yes articles. Let me remind you why that is. It's because of the way I defined yes docs. So the first articles are all from no docs, the articles that are not about Joe Biden. The second set are all about Joe Biden, the yes docs. And that means that order is preserved. Each row here corresponds to an article. So if I wanted to look at the tf-idf vector of the very first article, that would be row 0, the very first row of that matrix. Okay, and the very last article would be the last row. So one thing that we can do here that's going to be interesting is we can kind of zoom in. We could explore these bright areas, and I'm going to focus on this line right here because that little half line is likely to help us actually classify the articles. So instead of showing, actually, what does matShow do? Let's see what matShow does. That's about the same. Instead of focusing on the full matrix from tf-idf, I'm going to focus on a subset of the columns. So I'll look at the columns from 200 to 220. Okay, great. So look at this. This is very nice because the top half of these articles are out of class. The bottom half are in class. And this line is going to be a great indicator. Each column in tf-idf corresponds to a feature. In other words, a particular term in the vocabulary or a word. So that means there's some word. When it is in the article, it says it's about Joe Biden. When it's not, it says it's not about Joe Biden. And I can just see visually that there's probably one column left. So I think the column that we're interested in here is going to be column 218. In case this notation is new to you, the first colon here basically says I want to look at all of the rows. The colon basically means everything that could happen in this first index. And the 218 means look at column index 218. So the beginning is row index, the second is column index. This means all rows, and then column 218. And what we can do is we can look at our words list and see what word is word 218. Biden. So you can just see right away that actually makes a ton of sense that the word Biden is showing up in our articles about Joe Biden and not in the articles not about Joe Biden. Keep in mind, we have done zero machine learning so far. The only thing we have done is created a matrix representation of our data and been smart humans looking at it to find a particularly visually interesting feature that stuck out. All right, so let's see if actually training a model can be as smart as a human simply looking at an image. What I'm going to do first, I need to create an official set of labels for my data in order to train and test. So I'm going to have to import NumPy. It's traditional to call it NP after you import it. It's traditional to call your unlabeled data points X, and then to call your data points, that means the labels themselves, the values you want as outputs, we call those Y values. And I'm just going to get a one-dimensional array with zeros and ones. So this is my label vector. It's got 12 zeros and it's got 12 ones. This np.zeros 24 creates a vector of length 24, all zeros, and then the next line I set the last 12 entries to 1, creating the Y. It's technically of type ND array, but I'll call it a vector. Next up, let's import the train test split function from SKlearn. So what does the train test split function do? Actually, I think the help string for this one is not super clear. Its signature, it just takes a star arrays and star options. About the most useless Python signature you could have. And the best way to really learn how to use this is actually by example. Almost always, at least for me, I use it exactly the way I'm going to show you, which is I have 4 outputs called exactly xtrain, xtest, ytrain, and ytest. And I'm going to split my x and my y values. And then one common parameter that I didn't use is to determine the size of the split, but I just let it do its default thing. It's picked out 18 training examples and 6 random test examples. All right, and we can kind of see that xtrain has 18 rows, the same number of columns that it had before, and then the y values are just, it's simply a one-dimensional array of these zeros and ones. Okay, so now we're ready to actually train a logistic regression model. Again, SKlearn, great library. So in case at this point you're wondering if all machine learning people do is use SKlearn, no, that's not actually true. SKlearn doesn't do a lot with deep learning. It does have a multi-layer perceptron, which I would call a deep learning model, but it's basically covers a lot of the commonly used models pre-deep learning. I mean, they still are very much evolving over time. They are not out of date at all, in my opinion. But SKlearn is not the end-all be-all of machine learning. There are a lot of other tools. It doesn't really cover computer vision in depth, for example. It doesn't focus on linear algebra very much. It supports it, but it's not. There are a lot of important things that SKlearn doesn't do. It's sort of like your nice starting point for getting a good baseline model up and running. Okay, so let's train a logistic regression model. And in this case, I'm actually not going to change any of the default parameters. I'm just going to train immediately. I often get future warnings from SKlearn, and I have learned through experience to ignore them. I think SKlearn gives a little more warnings than is entirely necessary. Okay, so now we have a trained model. Let's see how it's doing. So what I'm going to do, well, actually, let me just show you what kind of output the predict probability function gives us. It gives us a two-dimensional matrix. So let's see, what is the size of X test? This is a length 6. It's basically a list of tf-idf vectors of the test documents that were not used during training. The output here is a set of two numbers because there are basically two classes. There's class 0 and class 1. So these are the estimated probabilities, or confidence scores is what I call them, that the document is in the given class. So for the first document, it's saying, well, with confidence 0.38, it's in class 0, or with confidence 0.61, it's in class 1. And these numbers are redundant. They always add up to 1. So you don't really need both of them. And what I like to do is to convert these to ones and zeros by basically casting them to integers. So I'm going to call the same function again. It's so fast, I'll run it again. It's very fast, right? Okay, so there's our predictions, and let's see what the actual values are. So in this particular case, it achieved 100% accuracy, which is pretty good. And I don't even really need to do any extra work to calculate that. We can actually get some more interesting things out of the model besides it being a 100% accurate classifier. What I can do is I can look at the coefficients. If you hear some snoring noises, my dog is snoring in the background. All right, so the coefficients are an ND array, n-dimensional array. And we can kind of get a sense of the shape of that array. It's a 1 by 1655 matrix technically, but really it's just one row. What I'm going to do is I don't like working with theoretically things that are matrices when they're really just vectors. So I'm going to call reshape, which will give me a one-dimensional vector. Okay, that's easier to work with. And then I can call argmax, that's finding the index of the maximum value in this list. It's 218. So immediately it's the same thing that we found before. It's the Biden word. Great. So we know that logistic regression picked up most strongly on what we also picked up as humans. But I'll show you that it's not just doing sort of a mediocre job here. What I'm going to do is look at the top, let's look at the top 10 words that most strongly indicated that the document was in class. So I'll explain what this code is. Argsort sorts this vector. It doesn't actually change the values. It sorts it, basically sorts a copy of it. And then it returns a list of the indexes. That's why it's not sort, it's argsort. It returns the indexes in the order of increasing value. All right. So in other words, because I've sliced it to get just the top 10 values, the last 10, which are the largest values, these indexes, they're not going to be meaningful to us as humans. These words here are these are the indexes of the words that most indicate that an article is likely to be about Joe Biden. So let's actually take a look at what those words are. So Biden is the most indicative, and then campaign, his voters, president, Democratic, he, Trump, Obama, Joe. All of those words make a lot of sense, right? Keep in mind, we trained on, what was it, 18 articles, only 9 of which were actually on topic. The other 9 were negative examples. Oh dear. Okay, I better finish up this video. Yeah, actually that's a great stopping point because my disk is about full. So it's just strong evidence that logistic regression works, which is awesome. Thanks for watching.